Good morning, everyone, and welcome to Mandalay Bay GH. That's the name of the room, and the name of the talk is Subverting Apple Graphics, Practical Approaches to Remotely Gaining Root. Got some very good information here from the team at Keen Security Lab. Before we begin, though, some quick notes. The business hall in Bayside AB throughout the day will have all kinds of great vendor expo sort of things going on. There's also a welcome reception there tonight from 5:30 until 7. Right now, happening all day today, I believe, is the Black Hat Arsenal. That can be found upstairs in the Palm Foyer. And then tonight at 6:30 are the Pony Awards, and that's in Mandalay Bay Room BCD, which is just down the hall. And then one final note, please make sure that any mobile devices, phones, iPads, laptop computers, whatever you've got, is on some kind of silent or vibrate mode, just to make sure we don't disturb the presentation. So that's it, and please give a good welcome to the talk. Thank you.
Thanks, David. So I will begin our talk. So our talk today is about subverting Apple Graphics practical approaches to remotely gaining root. So we use this title because actually we pwned OS X with root privileges twice this year. And from the year 2014, we actually also got sandbox bypass and successfully pwned OS X remotely in Pwned 2014. But I think as most of you know, that 3 of our privilege escalation bugs are relating to Apple Graphics. So today we will introduce Apple Graphics and explain why it is a very good attack surface and why it is dangerous. So about us, so everyone knows that we are currently Tencent Keen Security Lab, which is previously known as Keen Team. And in 3 years, actually, we got 8 Pwned winner titles. And this year, we pwned OS X twice with root privilege escalations. And one of the bugs got a Pony Award, Best of Privilege Escalation nominations this year. So today, we hope we can win it, but with very little possibility, maybe. Okay, so and this year, we also, Tencent security team got Master of Pwn titles this year. So let's begin our talk. So in this talk, I will first introduce Apple Graphics, and then we will introduce userland attack surface with CVE 2013-1804. And we will do a demo about that. And then Franco will talk about the kernel attack surface, and Marco will talk about the bug exploitation. And also, the talk will be wrapped up with a live video demo. Okay, so Apple Graphics actually contains 2 parts, which is the userland and the kernel land. So for a sandbox app, usually you call some IPC interface to the Windows server service, which is a daemon. And the Windows Server service daemon will actually call the IO kit, which is in IO accelerator family class. And this class is actually implemented by NVIDIA and Intel graphics. And for some apps like Safari or Chrome or some other browser, because of the performance consideration, then the sandbox profile actually allows directly calling to the kernel. This is for example, currently you need WebGL or something like that. So you need a better performance, so you can call them directly also. So if you look at the sandbox profile on OS X or iOS, you will find that both in the user mode and the kernel mode, the Apple Graphics components are allowed to call. So from the user mode, it is on the OS X, it's a Windows Server.active. And in the kernel mode, it's actually done by IO kit connection, IO accelerator. And you can see that I/O accelerator is actually an I/O service, and the I/O kit connection actually means that you can open all the I/O kit client, user client, which whose I/O service is I/O accelerator, which is very good. That means you can open up to almost 10 or more user clients. So now I will introduce the userland attack surface. So you can see that the userland attack surface, the Apple graphics is implemented by mostly by the MIG, and the MIG is Apple's IPC implementation, and the implementation is no more interesting than some other modern OS like Windows or like Android. And the implementation is two things that you need to remember. One thing is that it is done by calling mark message. And the second thing that it contains not only the simple message, but also some complex message, because you know, sometimes you need to not only send some simple message, but also you need to send something like send a port to another process, or sometimes you need to send a pointer to another process, so that kernel have to be involved to do the address mapping or the port mapping. So from the parameter of mark message, you can find that there is mark header bits, which the highest bit, if it equals to 0, it means it's a very simple message, and 1 means it is a complex message, which involves a port or OOL or something like that. So actually, there are 4 types of messages. One is simple message, which is very easy to understand, and the 3 other types of descriptor. One is port descriptor when you want to send a port, and the OOL descriptor when you want to send a pointer, and the OOL port descriptor when you want to send a pointer containing an array of ports to the remote process. So let's have a look at the Windows Server. So it has 2 private framework, and you can see most browsers allow to open one of them, which is Windows Server.active service. This service is actually implemented by Core Graphics framework, and another framework called Core is not allowed by Safari Sandbox by default. But later on, I will explain more detailedly, and you will find something interesting. And there are 2 sets of APIs. One is a client-side API, and another is a server-side API. You can find it, distinguish them very clearly by the name. The client side starts with CGS, and the server side starts with _X. And by its feature, you can categorize them into several ones. For example, window, majorly doing some window creation, window grouping, or something like that. And for sessions, it is session management. If you think it as a hacker, you may, for me, I think as this way, because before OS X line, there is no Apple Sandbox, and but at that time, Windows Server has a long history than the Sandbox. And after that, we may think of after the Sandbox is introduced, there may be some flaw or something that Apple failed to consider. So we began to think it. For example, if we need to bypass the Sandbox, the first thing we think is that move the mouse plus click. If we can simulate this operation, then it means bypass Sandbox, because we can move the mouse to the calculator icon and then perform a double click. And also we may do some set hotkey operation to set up our own customized hotkey. So let's do the real exam to see how they can be done. But we found that we are wrong, because Apple is not that bad. If we see the move mouse operation, it is still allowed from a Sandbox app. But if we do a click, then you can find it checks for some entitlement, and most Sandbox app doesn't have HID control entitlement, so it is blocked. and also the same situation for set hotkey. And also, we may need to think about some Windows-related API because on Windows system, Microsoft Windows, we actually have a lot of UAF issues relating to window. For example, you can set up a callback to free a window, and after that, it is used again. But maybe on OS X, there are similar bugs. But when we perform the code audit, we found that many of them have some check like connection holds right on window check. This check actually only allows the window creator or the window owner to hold this permission. And if you are not, then you are blocked by this check. And in history, I think there are many tricks to bypass this check, but now it's harder. And another thinking is that many other API of the window-related API doesn't have that check, so it is very worthwhile for further code auditing or fuzzing to find a more interesting bug. And we need to also emphasize that why we choose Windows Server, because is it running in root? Of course not. Is it running in user account? Of course not as well. So what's the account for Windows Server? Actually, it's nothing. You will find that this account has very little permission. But Windows Server is actually a privilege chameleon. It can change privilege, and I will illustrate it by 3 bugs. The first bug is actually the bug we used it at Pontoon 2014. At that time, we audited an API called XCreate session. And so this is a server-side session which allows you to create a new login session. And in this new login session, it will by default to fork a process, which is login window, and then set the UID of that process to the current user's process. So it's very good. And that API allows the user to customize that path. So that it means you can bypass the sandbox and run a sub-process on the arbitrary path and the file and with the user's context, which is perfect. And after Pontoon 2014, actually Apple did some check for the fix. They fixed that by add a sandbox check API for all sandboxed app. So from a sandboxed app, you are not able to call this function again. It's very effective, and we cannot bypass it. And for now, you can see that this API happens to everywhere, and make me very tired. And it is very obvious that Apple realized it's dangerous in core graphics. And now we need to explore another private framework, which is Coarse Core. Coarse Core offers more complex operations like animation or multi-layer handling. So, but the sad thing is that Safari Sandbox doesn't have that rule, so that you cannot open it directly. But is it that does that mean that you cannot open it? Actually, the answer is no, because as we just mentioned, there is a method called there is a message. The type is a port descriptor message. It allows you to send an IPC to the remote process, and maybe the remote process will have the privilege to open that port, and then it will create that message to send the port back to your process, so that you duplicate that port into your process. Yeah, and in OS X, the API exists, which is CGS create layer context. And if you call it, you will get a port, mark port for Coarse Core. And then from now on, you actually can call every APIs in Coarse Core, and you will find it's very good because you find a lot of logical issues, like you can set, you call this set message file to append some content into arbitrary file with arbitrary path. But the privilege have to be Windows Server. But if you check this bug on iOS, you will find something interesting. I will not mention it here. And for now, we got two bugs. One make you to escalate to the current user's context, and another makes you to be Windows Server privilege. And now I want to be root. So in this year, we use CVE 2016-1804, which is got the Pony Award nomination. And the bug actually exists in set global force config API, which did two CF release operation very close, which is a double free bug. But let's think about whether it is exploitable. So if you want to exploit this bug, several problems must to be solved. One is that you have to fill in the data into two CF frees. This is the first problem. And second problem is that you have to do a very effective heap spray in 64-bit process. And also there is other thing like ASLR, ROP. It looks like very hard to exploit because the two frees are very close to each other. There is less time window. And another thing is that you can see all core graphics API actually runs in a single thread in a server loop. So you cannot use any of those core graphics API to fill in the data. And also, actually, we give up this bug for several days because we think the successful rate is very low, but it depends on something, which is that it's a very legacy double free problem. If you free a memory twice, will the process crash immediately? The answer is yes, if you use malloc API. But if you use CF, the core foundation version of the API to alloc and free, actually that's a totally different story. It doesn't crash. So we can change our strategy. We can make two threads. One is because we just mentioned that we have another framework called Quartz Core, which runs at another thread. So we can make the new strategy, which is we can do in thread 1, we try to trigger the bug again and again. And in thread 2, we try to allocate the memory with the same size. And if it failed, nothing happened. But if it succeeds, then we may got the code execution, which is very good. But the API must meet the following criteria. For example, the data you fill have to be 0x30 bytes. And the other that every byte, at least the first 8 bytes of that structure must be controlled. So what kind of message we can think of to try to fill? Of course, OOL message is the best option because port descriptor, of course not. And the simple message, it is hard to find a very good candidate. And you have another bad news, which is there is only one OOL descriptor message on the Quartz Core API, which is X register client options, only one. So that's very bad. And let's audit this API. Actually, this API accepts a serialized prop list because sometimes you need to send a very complex message from process A to process B. So for performance consideration, it actually do a serialize to make a CF dictionary to plist binary format and send it to the target process. And in this process, you actually some complex operation will be handled. So you will find something very interesting. And the first thinking we are considering is that we want to try to fill in with CF data, CF string, or CF blah, blah, blah. But we find that is not feasible because when you send those messages to the target process, actually those are considered as a constant, which is that the metadata, the real data is actually inlined in that struct, which means that first 8 bytes is also always the metadata of those CF message, which is very bad. So our last hope is the process itself of the deserialize. So you can try to audit this function, and maybe in this function there is some internal struct which created and then free it immediately. So for this kind of operation, it is also useful because we don't rely on the persistent data, but just some temp data is okay. And then we try to audit this function, and finally we found if we pass the Unicode string, then we will have this kind of operation. Like in this line, it try to allocate a memory with the bytes that you can control, and then it copied the content of the Unicode string into that buffer and then free it. So with this primitive, actually we have a very well-controlled buffer with controlled size. And even it is freed, the content of that buffer remains the same, so it's perfect. So we can change our adjust our strategy to use this logic. And finally, we got the control of one register, which is good. And the next thing we are thinking about is heap spray. So we do a simple test on OS X, and we found that the memory is very random, which we need maybe 1,000 gigabytes, 1 TB for a reliable heap spray, which is very bad. But when we try a bigger allocation, then we find the address is less randomized. So in this case, spraying will be very reliable. And we need to think of the following criteria when spraying. One thing is that the memory have to be persistent in memory. And also you need a very large block of memory because large memory allocation is less randomized in OS X. And also you need a OOL message because only OOL message allows you to do this kind of operation. So finally we got a very good candidate, which is CGX set connection property. So in this API you can find that it checks whether a global dictionary exists. And if it doesn't exist, it will create a new one. Otherwise, it will set up the value and the key pair. And the key can be unique, and the memory will keep growing. You can call this function again and again until the memory grows. And the last thing we think about is ASLR. But ASLR in this case is very easy because in OS X it shares with Safari process. The base address of most frameworks are the same. So because we started from a remote Safari exploit, so ASLR is not a problem. And the code execution is also not a problem. For more information, you can refer to this link. And the last thing, whether this bug can be a root privilege escalation, the answer is yes, because when you check this process, actually the UID is always root, but a Windows Server is just its EUID. So considering that you have remote code execution, you can execute arbitrary arbitrary code. Then you can just call set UID to 0 to set its EUID back to root. So I call this kind of mechanism privilege chameleon, which is very good. So we got 3 different bugs and 3 different privileges. And lastly, I will hand it over to QB for a demo. Oh, fine.
Okay, I will show a demo about this Windows Server exploit I use in the Pontoon this year. The target we attacked in this video is a virtual machine about with the latest OS version at that moment. And the whole process contains two parts. One is the Windows Server exploit, and another one is the Safari exploit. And now our server is listening and preparing to send the payload for the Windows Server. Then the web content process will try to fill in the double free field and trigger the UAF again and again. Once we success, so we can't see any change on the screen, so we select to show with a remote share. And okay, finally we got a root share. So next, Franker will talk about the kernel attack service.
Check. Okay, hello everyone. And first I need to apologize because I found that Shanghai is much more hotter. It's much hotter than Vegas, so I caught a cold, unfortunately. But I will try my best to explain this presentation in a clear way. And Liang and QB has explained and demonstrated our userland exploit on the Windows Server. And now I will do an introduction and analysis of our kernel exploit with the bug from the Safari sandbox, so that we can get a complete control of the system. The kernel attack surface we researched on is mainly the IO accelerator surface family. The IO accelerator surface family is an important class or important service in the Apple Graphics kernel driver system. And this interface is involved in almost every rendering operation that it will create a window in the OS X. It will create a you want to render some video, and then the accelerator surface is a must for your operation. But the interface, as Liang has described in previous slides, that in the ancient times, there are only Windows Server who will invoke or cause the IO accelerator surface function from user space. But after Apple opens up this interface for other sandbox applications, there may be some problems, and luckily we found one, and which is the CVE 20161815, the Blizzard, which we used to escape the Safari sandbox to gain a kernel privilege. The IO accelerator surface actually exposes many interfaces through the external method function, and there are actually we use about 6 or 7 external methods to complete our exploitation. And there are the first 4 key functions in this IO accelerator surface. The first is set ID mode, and the second is surface control, and the third is the surface lock options, and the fourth is the surface flush. The set ID mode is responsible for the initialization of the IO accelerator surface, and user mode applications provide a presentation type, which is an integer and will be interpreted in a bitwise format by the kernel driver. And when you call set ID mode on the newly created IO accelerator surface, the buffers are allocated, and the relevant frame buffers connected with surface are also reserved. This interface must be called prior to all other IO accelerator surface external methods to ensure that you got a valid IO accelerator surface to work on. And another important function is the surface control function. The surface control function it gets the input from user space, and the user space can specify basic attributes for the current surface. The most interesting one, or the most important one, or you can see also the most basic one, fundamental one, is the rectangle of the current surface. That you want to draw how big a surface and how large surface and the coordinate of the surface on the screen, on the physical display screen. And the surface lock option is also an important function, because that if you want to submit your surface to rendering, you must lock it first. And the surface lock options is an external method in the IO accelerator surface to receive some lock options to specify the lock behavior of the IO accelerator surface. And finally, there's another function named the surface flush. It is related to the double buffering and the triple buffering of the graphics pipeline. And if you call surface flush on a double buffer back the surface, then it will exchange the backup and the current buffer. And some surfaces have triple buffering support. So if you call surface flush, they are more complex process, and we will not elaborate about detail here. And also, after these four basic functions, we also have a basic rendering unit, which is in the, not only in the IO accelerator surface, but also in the IO accelerator subsystem. Is an 8-byte rectangle structure with a field specified in the surface control function. Actually, it's not hard to understand that to specify a rectangle to uniquely identify its location and its size, you must provide the x coordinate, the y coordinate, and the width and the height of the current rectangle. For typical graphics pipeline, and I'm referring to the picture of the OpenGL rendering pipeline, and you can see that first, end client supply a vertex data, and the vertex data goes through vertex shader, and it is rasterization, and then goes through rasterization, and finally it goes through fragment shader to get its color, get some beautiful colors to paint, and finally it's drawn on the frame buffer. The OS kernel graphics pipeline is not so complex as the OpenGL ones, but there are still some critical steps, and one of which is the rasterization step. The rasterization step contains the bleed operation, and the bleed operation actually contains a vulnerability we found. And also, I would like to introduce another additional surface that is also relevant to this exploitation in the IO accelerator surface. The first one is set scale, and the second one is submit swap. Set scale actually provides the end users, end clients in the user space to specify a scale factor, so that you can scale your window from it. For example, you would like the window to be twice the big as the original size, or twice the size smaller. And you can call the set scale function to specify a scale factor. And the surface holding joint region can be scaled with originally a rectangle region to form a rectangle pair. And in the IO surface, it is contained in a structure named the rectangle pair T. And an interesting observation is that originally we supply the surface rectangle size at the int16 integer format, but after surface control is called, after set scale is called, and when we call surface control, this rectangle is transformed to a representation in the IEEE 754 format, which is a float number. And finally, after these steps, we will provide the rectangles from user space, and the rectangles are scaled and combined to form a pair. And finally, we call submit swap to submit a surface. And the submit swap will do additionally a normalization on this, which is the bleed operation, actually what the bleed operation does, and it will finally submit it to the GPU. An important parameter for the bleed operation, which is the function bleed 3D submit commands, is a bleed param T. The bleed param T is actually a very big structure. I believe it has hundreds of bytes, and we use the reverse engineering to deduce some fields. And the most interesting two is the two ints at offset 14 and offset 34, which is the target surface. The target surface is usually the physical surface of the hardware, and the target surface width and height. And the pair we mentioned before, that is a rectangle pair T, and the bleed parameter T will be submitted from submit swap to the bleed 3D submit commands. The bleed 3D submit commands is an implementation in the Intel graphics to do the bleed operation. And as we have seen before, that user space applications can provide different logical surfaces, and this function need to normalize them as a valid rectangle to be processed by the GPU. So it will crop and resize different incoming surfaces to match what the GPU is happy with. And after normalization, two flashing rectangles will be submitted to GPU via the bleed rect list function. So there is an overflow in this bleed 3D submit commands. And as we know that from reverse engineering, we found that the OS X graphics calling system, it only accepts rectangle in a range like 00, 4000, 4000 in a hex format to draw on the physical screen. However, as we have seen before, a logical screen has a field of intersecting format, and it is a signed integer, so that actually it can represent numbers at a range like negative 8000 to positive 7FFF. So the bleed function needs to scale this logical rectangle to fit in the special range, or the GPU will not be happy with this rectangle. So now let's dive into the disassembly and the decompiled code of this bleed 3D submit commands. And first, we can see that it checked for the current surface, which is the logic surface white and the target surface height. And if either of them is larger than 4000, so at Houston, we need to scale the rectangles now to be accepted by the GPU. And first, it allocates a temporary buffer, which is a vector. The size is decided by a height divide 4000. And it hopes to store the project normalized rectangles in this vector. And the target surface vector, as I have stated before, that it comes from a full screen resource. Which means that it is decided by the physical screen resolution. For a non-retinal MacBook, it has a resolution of 1440 multiplies 900. And so for this MacBook Air model, its height is 900. But as we know that even for Retina Macs do not have a screen resolution that have a larger height than 4000. And even for 4K screens, its height is still smaller than 4000 in hex format. So we can see that the vector array allocated here always has a length that is fixed to 1. And these two figures actually illustrate how a normalization occurs. And the rectangle is the target surface to be drawn on, and the green rectangle and the blue rectangle are two logical surfaces that is provided by user, and it will be normalized to be drawn on the target region, which is the target surface. And then let's go through this bleed 3D submit command function, and we found this whole bunch of shit. And it is because that there are many floating instructions involved in this function. As we know that because you have called a set scale to convert the rectangle's attribute to a float number, so there are many floating instructions involved here, and the IDE hash rates actually cannot properly handle this bunch of things. So we go through this disassembled code, and we rewrite the algorithm to a more like a clear format. But you can see it's still not very short, but actually. If you understand this algorithm, the thing it does is actually not very complex. It just for example, we have stated that there are two rectangles, two logical rectangles that is supplied by the user space. That one is the original one, and the other one is the scaled one. The two rectangles, the bleed 3D submit command function will calculate that it need to decide on the scale factor, so that the two rectangles, as you can see, these two, like a green rectangle and a blue rectangle, they need to both be normalized into this physical region. So they need to be normalized using a same scale factor. And if the two rectangles are already in screen, as you can see in the first if statement, then it will not do a normalize. They just preserve this rectangle. But if it have a right boundary or left boundary out of screen, it will do some substantial options. But for our bug, and we can see that at line 1, it accesses vector based on index that is calculated by divide rectangle, the second rectangle's x coordinate to 4000 hex format. But as we remember that the vector array only have a size of fixed 1, but the x coordinate of the second rectangle can be decided by the user space. So there is an obvious OOB access condition here that the vector is retrieved and accessed after. And we can see that this rectangle is accessed, is retrieved and accessed at here. That we can see there the vector add function call, and the rectangle's attributes is combined to a pair, and the IG vector add function is called on this OOB location. So, as a conclusion, that this code implicitly assumes that if the width is smaller than 4000, then the incoming surface height will also be 4000. And this is true for Windows Server, I believe, because Windows Server is also written by Apple programmers, but not for funky clients like us. For example, we can supply a surface with a rectangle, with the second rectangle's x coordinate set to value larger than 4000. So the line 1 will go out of bound just after this vector that it accesses the second vector, and then IG vector add function will be called on its OOB location. And after some testing, we chose to use this 4 attributes that 4141, 4141, FF as a rectangle, and it will be normalized to y coordinate 16705 and x coordinate 321, and height and length both to -1, and trigger 1 OOB write, and then it will bear out in the while condition. So we have an OOB write on this IG vector add, but what is the IG vector, and what does IG vector add does? We need to revisit the IG vector structure. The IG vector structure is actually 24 bytes structure with 3 fields. One is the vector's size, and one is the vector's capacity, and the third attribute is the vector's backing storage pointer. And when a vulnerability occurs, we can see that the vulnerable allocation is in the KLOC 48 zone. And the first 0x28 is the size of this allocation. As we can see that the new operator is called, and the new operator will store the size as the metadata at the head of this allocation. And the one, it deduces that the vector, the new array operator allocates an array of size 1. And finally, the 3 size capacity and storage pointers follows after this metadata. And this is the benign and valid IG vector. But unfortunately, when the OOB occurs, it goes right behind this benign IG vector, and the dead beef and the blue rectangles blue regions are interpreted as another fake IG vector. And the IG vector add function, actually, we can see that we can utilize this function to achieve like an arbitrary write anywhere, but the value is constrained, and we cannot write arbitrary value. As we can see that RCX is written to the RAX plus RSI plus 18 and 10 and vice versa, and but RCX is retrieved from R14, which is the rectangle attribute. And if you remember what I've said in the previous slides, it is a floating number. So we got an OOB right, and in this KLOC 48 zone, and we need to do a heap function to ensure that what follows after this benign block is the content that we can stabilize, control it. Previous methods like VMAP copy and open service extended are known methods to prepare the OSX and iOS kernel memory. But there is a problem for our exploitation because we are dancing in the KLOC 48 zone, and there is a very annoying thing called IO bug port. Our mark port is also have a size of 48, and it will fall also in this zone. And we need to get rid of it to get a stable heap control. But previous methods have their fallbacks, and the OL message spray, which constructs a VMAP copy in the kernel heap, the head 18 bytes is not controllable, but we definitely need control over the 8 bytes at the head, 8 bytes of set position. And IO open service extended have a massive side effect in this KLOC 48 zone because it will produce an IO mark port in every opened service connection. So we are presenting a new method called the IO catalog send data. And I will not talk about the detail here, and if you are interested, you can refer to our blog post due to the time limitation. But to use this method, you can just pass in an XML and prepare your spray content in this array, like in an OS string, OS data format. The good thing for our catalog send data is that it will not cause side effect in the KLOC 48 zone, and you can just use the master port to prepare your memory content in the kernel, and you can control all the content of the OS using OS string or OS data. So finally, we come up with the following steps in the KLOC 48 zone. First, we spray about 8,000 combination of one 48-byte VMAP copy and 40 OS strings in one IO catalog send data invocation, and the content of which is prepared and controlled by us. And then we free the VMAP copies in 1/3 to 2/3 paths so that we can dig holes in the allocation. And finally, we trigger the vulnerability in the please 3D submit commands, and the vulnerable allocation will fall in the hole we previously left. So these figures, I think, will illustrate the steps more clearly. First, we have the OER message and the control blocks specified by the catalog send data, and then we kick out the OER messages, and so that we can leave holes in this content. And then we trigger this please 3D submit commands, and it will allocate buffers in the free address due to the nature of the OSX kernel zone allocator. So that we need to ensure that what follows after this 48 block, what is filled after this IG vector is content we can control, and so that we spray like 50 controlled blocks, so that we hope that IO mark port will not fall right after this vector array to break our exploitation. And if you spray more blocks, and there's less chance that IO mark port will appear right in the head of these controlled blocks. And we use this approach to get about 100% stability of this KLOC 48 function. So after these steps, you get unstable OOB write in the KLOC 48 zone, and you can use this OOB to overwrite arbitrary address in the kernel, but the value you have write, but the value you can write is constrained to a float number, and also in a range that is not very big. So you still need additional work to turn it into RP control and info leak. And this figure will give you an overview of what we do next. And actually, we have presented in the recon slides, so we will not talk about very much about detail here, but Marco will give you a brief introduction on this. Thank you.
So, like Flanker said, we will give a brief introduction for exploitation. So we have an arbitrary write-where primitive, but our value that we write is constrained to be a float, and so we use this arbitrary 4-byte override to write this value BF80000, which is a valid float, to overwrite the less significant 4-byte of service pointer of IO user client. So as you can see at the bottom, there is this pointer before and after overwrite, and after the overwrite, this pointer will point to our controlled heap location. So like many people may know, on OS X there is kernel ASLR, so we need to bypass it. We will abuse some external method of IG Axel video context, which is a IO user client for graphic to bypass KSLR and then gain instruction pointer control. So we choose to overwrite the accelerator field, which is at the offset 528. Remember this number because we will use it again. And we'll point it to our controlled location. And then after we abuse this external method, get hardware settings, to leak 1 byte at a time to user space. And first we read the vtable, and then we follow this vtable to read OS object release text address. And in this way we can obtain the KSLR slide. So as you can see here, there is some decompiled code from the method, and the accelerator is pointing to our location, and the HU array is actually returned to user space. So we get 1 byte of info leak. This is a diagram of the info leak. And now that we have KSLR slide, we can rebase our ROP chain, and we can start executing kernel. So at the end of our ROP chain, we'll invoke this nice OSX method, which is KUNC execute, which is communicating with a user space daemon, and it will allow you to execute arbitrary binary as root. So in this way, we can bypass SMERS map and the SIP and spawn a root OSX calculator. So the last piece missing is gaining instruction pointer control. Again, we will abuse another external method of IGAxel video context, in particular of its superclass IOAxel context 2. And this method is called the context finish. And as you recall, we overwrite a pointer at offset 0x528. So here it's the disassembly of the method. So basically the pointer at the offset 528 is taken, and then we do this virtual method call and we start to execute. So for time constraint, we have to leave the details for the white paper, but we can do a cool demo. And interestingly, you cannot launch a OSX calculator with sudo. So if you see a root calculator on your system, you are being pwned.
I will play a video, and the video itself is quite self-explanatory. Credits to Hans Zimmer for this background music. Okay, thank you for watching the video.
Okay, so because time is tight, so we have to stop here. So before we finish, we would like to thank the following guys. The first one is Wu Shi, who is the head of King Security Lab. And the second is Wind No, who from Pangu. And Luca is very famous on Twitter, and we discussed a lot in the website, in the Twitter. And the UFO talent is a friend of Flanker, and he gave us a lot of advice about how to reverse engineering the graphics sheet. Okay, lastly, thank you.